Welcome to my YouTube channel Raise Acad. Myself Yash Mishra, and today in the YouTube lecture series of thermodynamics we will be seeing one more question in which there are some conditions given for a particular cycle. So we will see them one by one. So in this question there is an aircraft engine which is working on a Brayton cycle, okay, and in this there is a working fluid which is air, okay, and the pressure ratio is given and the heat input which is there, it is given, okay. And what we have to determine, we have to determine the net power and net thermal efficiency. So these are the two things which we have to determine, okay. And the Cp value is given as 1.005 kilojoule per kg Kelvin, and the K value is given for this process, isoentropic process it is, and K value is given as 1.4. Okay, so these are the two things which are given, and pressure ratio, heat input, and the temperature is also given, and that these are the two things we have to determine, net power and the net thermal efficiency, okay. And the assumptions we have here are the steady state operating condition exists, and the standard air assumption is applicable, and the kinetic energy and potential energy changes are negligible, so that we can conserve the energy here in this situation since the energy changes are negligible, okay. So initial kinetic energy, potential energy is equals to final kinetic energy plus potential energy, okay. So energy we can conserve here, okay. So air is an ideal gas with constant specific heat, okay. So Cp value it is given as 1.005 kilojoule per kg Kelvin, and working fluid we are taking as air, okay. And we have to determine the net power and net thermal efficiency for this process, okay. So just consider there is a particular type of cycle in which we have to determine the net power which is being given, or the net for the power what we do we calculate the net work which is there, and we add the net work and we get the net power, okay. Thermal efficiency formula, we just divide the work with the given heat, okay. So this is the approach, standard approach which we follow. So in this question also this only approach we will follow, okay. So moving further, so this is the diagram of the process. So we can see that here the initial temperature is given as 273 Kelvin. This is a first point, second, third, fourth. So this is a particular cycle. T versus S diagram is given, okay, and this is an isoentropic compression process, okay. So 1 to 2 isoentropic compression. So this is a isoentropic process, okay. So the T versus S diagram for this process is given, and the initial temperature is given as 273 Kelvin, and the Q, from here the Q heat is inlet, from here 4 to 1 heat is outlet, 2 to 3 heat is being given to the process, okay. In the process of 1 to 2 it is an adiabatic process, so no heat is given, no heat is coming out of the coming out to the surroundings. So it is a, this indicates that it is an adiabatic insulation which is there in the process from the 1 to 2, and 3 to 4 also adiabatic insulation is there, no heat is being going in and no heat is being coming out of the system, okay. From this 3 to 4 heat is only coming in and going out from 2 to 3 and 4 to 1. This is a T versus S diagram which is given. And also for the isoentropic process we know that the temperature are related as T2 is equals to T1 R to the power of K minus 1 by K. So this we have to remember that T2 is equals to T1 R to the power of K minus 1 by K. This we have to remember. R value is 10 and T1 value 273 which is given, and the K value was 1.4. So K minus 1 came out to be 0.4. So 273 is equals to 10 to the power of 0.4 upon 1.4. So T2 value came out to be 527.1 Kelvin, okay. So this is how we calculate the T2. Just we have to remember this formula for the isoentropic compression process. So this is nothing else from the polytropic process. V to the power of n is equals to constant. From there only these are formulas came. This we have to remember, okay. So for the heat addition, what we will use for the heat addition, this Q in is equals to capital Q which was given upon the mass flow rate. So capital Q was 500 kilowatt upon mass flow rate which is 1 kg per second. Mass flow rate was given, M was given, as 1 kg per second for this process of 2 to 3. Okay, mass flow rate is 1 kg per second, and this capital Q is 500 kilowatt. So we will put the value and we will get Q in as 500 kilowatt second upon kg. Okay, this is the value of Q in which we will get. Okay, and we know that the Q in is related to temperatures as Q in is equals to Cp T3 minus T2. So how this Q in and temperatures are related? Q is equals to Cp delta T. So Q in is equals to Cp into T3 minus T2. Okay, so it is also related as this Q in will be Cp into T3 minus T2, Cp delta T, T3 minus T2 for this process. As Q in for this process is 0, for this is also 0. For this Q out will be Cp into T4 minus T1. So Q in will be Cp into T3 minus T2. T3 is equals to, so now here from here this Q in by Cp. So Q in came out to T3 came out to be T2 will come here, but Cp will go down. So T3 is equals to T2 plus Q in by Cp. So this is how we will calculate this T3. Okay. So moving further, we will put the values of this T2 and Q in and Cp. T2 value is 527.1 and this Q in is 500 upon Cp, which is 1.005 kilojoule per kg Kelvin. So we will put all the values and we will get the answer. Okay. So what will be the temperature at the exit? The temperature at the exit will be related as T4 is equals to T3 1 by R to the power of K minus 1 by K, and temperature at exit this T4 we have to calculate. So T4 is equals to T3 1 by R to the power of K minus 1 by K. Okay, so this 1 by R is 10, so 1 by 10 to the power of 0.1 minus K minus 1 is 0.4. Okay, so 0.4 upon 1.4, T3 value is 1025 Kelvin. Okay, so we will easily get the value of T4. Okay, so moving further, so applying the first law to the adiabatic turbine. Okay, so adiabatic turbine Wt is equals to Cp into T3 minus T4. This downward. Okay, so from here this W turbine will be Cp into T3 minus T4. Okay, so the Cp value we know 1.005 into 1025 minus 530.4. Okay, so T3 T4 is this, since this is an insulated and adiabatic process, T3 to T4. Okay, so how this work done for the adiabatic process we will determine is equals to Cp into T3 minus T4. Okay, so this is an adiabatic process 3 to 4 and also 2 to 1. Okay, so for this process of compressor, this is a compressor, this is an adiabatic turbine, this is a compressor with the adiabatic process. Okay, so for the adiabatic process we know that the work done is Cp into T2 minus T1. So we will easily get the what is the compressor work done, Cp into T2 minus T1. T2 value we know, T1 value we know. T1 value was initially given, T2 value we calculated. Okay, and Cp value was also given 1.005. We will put the values, we can easily get what is the work done for this compressor. Okay, so this was the approach we followed for calculating the work done for the turbine, adiabatic turbine, and work done for the compressor for the process of 3 to 4 and 2 to 1 for the process. Okay, so net power produced will be M into Wt minus Wc, work done by the turbine minus work done by the compressor. Okay, so this will be the net work done or the net power produced. Okay, net power produced is nothing else but net work done of the system or the net work done of the process. This is how we will calculate the net power of a particular process or the particular cycle. Okay, so net power work done will be M into Wt minus Wc. So M is 1, Wt is 496.6, Wc is 255.4. So this is how we calculated the net work done. Okay, or net power. So thermal efficiency is nothing else but W net by Q in. Okay, so W net we will calculate as 241.2 and Q in was initially given as 500. So we can easily get what will be the thermal efficiency for this process. So these were the two things, net power and net thermal efficiency. So these are the two these were the two things asked, and we calculated the both of them. Okay, thank you.